Or middle. Okay, so hello everyone. My name is Muhammed Abdulbasit. This is and our project was, or our topic was DNA storage simulator. So here are the papers, the four papers: frame D, DESP, DNA fountain, and shortmer combinatorial encoding. These are the links to all the papers, and the authors are all underneath them as well. So an introduction. So everyone knows the world is generating digital data at an exponential rate. I'm sure you guys have all experienced this before. Maybe your phone iCloud storage or anything has like ran out before. So I'm sure you guys have experienced like having a shortage of data. So traditional storage technologies like hard drives are struggling to keep up. And one alternative is DNA. And the reason it's an alternative is it has extremely high density and can last thousands of years. So a little bit more about why DNA. So obviously it has extreme storage density, like I just mentioned, petabytes in a gram. And here's here's kind of an image here to show you how many bytes are in this, and this only goes up to terabytes. So the highest it can go is all the way up to petabytes. So it's really an extremely high storage density compared to like the other thing that we have like hard drives or anything. Um, and has long-term durability. So it can last for thousands of years in the proper conditions. Um, I guess an improper condition would be like extremely high or extreme temperatures that could cause some issues. But of course, there are some challenges such as errors during DNA synthesis, storage, and sequencing, which we'll get into a little bit later. Um, I was a, I think pretty much like most of normal the data types you could store, like audio files, image, text. I'm pretty sure all of that you can store. I didn't see any limitations for what you could store in terms of the data. Yeah. So here's like an overview of the tools. So frame D, it's kind of just like a very short overview. So it's a simulation framework. It's a modular platform to simulate DNA storage and evaluate errors. DNA fountain. This is not really a framework, but an encoding method. And it practically encodes data into DNA with error robustness. This is another error simulation, so similar to frame D. Um, and the key idea with this is that it's easy to simulate and study errors during the whole process. So it has errors through every single process, and this is more easy to set up. Whereas frame D in the beginning, it's like it's a little bit more complex, but you have a lot more control over it. And then short-mer encoding. This is very niche. This is high density encoding, and the key idea is that it packs more information into each molecule by combining short-mers. So here are some of the advantages of FrameD. It's a modular platform, like I mentioned, can configure encoding error, injection, and decoding modules easily. It has full process of the simulation, models encoding error, and DNA storage pipelines. It allows for flexible testing, so it allows different error correction algorithms to be swapped out. So if you wanna change it, it's easy to change it and see which algorithms give you least amount of error. And it's also effective, um, cost and time effective by allowing you to simulate the errors without actually doing the experiment. So obviously that's going to save you a lot of money and time instead of doing the actual experiment. And then it's also used as an optimization tool to refine the error correction algorithms and sequencing strategies efficiently. And then the next tool, DESP, this stands for DNA Storage Error Simulation Platform. So yeah, like I mentioned, this is mainly for error simulation. It's kind of what it focuses on. So the first step is like encoding. So the problem here is that some strands can just disappear or never get read. That's where one error can occur. Um, Errors can be introduced across all stages, and then at the end, once you try to decode, once you try to read the from the DNA, there's error correction to see how well to see if it can be fixed, because there's going to be errors. So here's some of the error types. So during synthesis, when you're building the DNA strands, there can be errors like I said in the beginning. Some strands they just never get read or they just disappear. And then during storage when you're storing it into the DNA. There's errors that can be introduced there as well, and just having it over a long period of time, eventually that it's going to degrade a little bit. So there's some errors that get introduced there, and then sequencing once you're reading it as well, there could be errors. So in all three stages, there's going to be errors, and at the end, you do some error correction to see how well your algorithm can fix the damage that's been done, and then
All right, the third tool is DNA fountain. So this is an encoding technique and encoding algorithm. So if we're talking about its robustness, it achieves like reliability close to the theoretical limit. It's quite efficient. It approaches the Shannon capacity, which means you can store as much data as you can. And third, it's high density. It can store up to 15 petabytes per gram of DNA. This is far above the previous records. So it's just a strong proof that encoding techniques like fountain code, as well as suited for DNA storage. And then fourth one is short-mer encoding, and its key benefits are it has also high density. It can store up to 6 times more data per synthesis cycle. So each DNA gram that you encode, so that's just one cycle. Yeah. And then the second, it is error resilience. While testing, we didn't face a single error while using this algorithm. And third is the proof of concept. While the authors that did this, they made this tool where used two molecules to synthesize, and they successfully decoded them successfully. And this just a side-by-side comparison of the pros and cons. You can see the frame D has modular, customizable sports large-scale simulations. And talking about the cons, it needs high computing and setup that is also complex. And the DNA fountain, it reaches max density, efficient to missing strands, flexible encoding, but it also has like difficult uh, encoding and decoding steps that need extra error correction. The DESP is a full pipeline of error simulation, so it helps testing different errors. Also, the cons are accuracy depends on model quality and setup is detailed. Talking about the short-mer encoding, it is high density, so that's the pros, and it needs advanced synthesis technology, complex decoding, higher sequence depth. Short-mer is the algorithm that they use to encode and then decode the synthesis, each DNA strand. No, it's just a DNA or all like sequencing and then encoding that. And this is just side-by-side comparison of each tool that we're using. So FrameD and DESP are simulation tools just to simulate errors and how we can decode then after that. And then DNA fountain and shortmer for encoding to store high DNA data, and then it has technical limits, complex encoding. So these were the results that we uh, found out while testing. So we found out that the shortmer encoding stored the most data. So it was 1.80. The storage density is how much you can store. So the formula that we used was total bits encoding over total number of nucleotide synthesis. So it just tells you how many bits of data you can store per single DNA base. Why this is 1.8 total bits encoded over total number of nucleotide synthesis. So that's equal to storage density. And then we used error tolerance to measure how much tool can tolerate an error. We found out DSP is the has the most tolerance, and then we found out the encoding time and decoding time for each tool. We found out that the DNA takes the largest time to encode and decode per MB. Yeah, text file. Just like yeah, you get encoded into DNA sequences, and then we decode that back.
I see. So if there's like E or X, to only ACGT.
ACGT, correct? Yes.
And character will be translating to
Around 30, 30 to 5.
each character will be translated to 30.
and number of lines of each DNA.
Some of them had graphs as well. I think SP, I think that had some graphs as well. We used that as well. But yeah, I mean,
And then you produce DNA text into what?
Back to not original form.
But do you impose some errors in them?
Yeah.
Do you
Mhm.
emulate those errors?
yeah. So some of them, I think we'll go into like the next slide. We'll talk about a little bit more how it works, how we inject errors.
So this is just a graph of how that story density is compared on all of those tools. The frame D is lower than then the DNA fountain tool, and the shortmer is the highest, has the highest story density. And this is error tolerance for each tool. So this shows that DSP has the most error tolerance of up to 95%. And this is just encoding versus decoding time, how long it takes for each tool to encode and decode the data. Because the DNA fountain has the highest decode and is redundant. And this shows the error density in the different format. Yeah, error tolerance is over there, and then stored density is there. Yeah, how much you can tolerate errors while simulating.
The tolerate
You can tolerate up to 92% of errors while having almost 1.4.
So it means
Five.
even if you introduce 90% of errors, it still
No, I think-
can
I
capture
think-
them correctly.
I think what it means is when you insert like substitutions, deletions, and all that, it still maintains 94% of the original data once we read it.
Okay, but it doesn't say anything about the error itself. How much the error was imposed in the text.
Yeah, yeah. I guess how much error was it?
So it retains 90 something.
Yeah.
Of the text all the time,
All the time.
regardless of the error.
Right.
All right.
And this is just an ease of setup. How easy was it to set up the code that they provided? The frame D was kind of complex. We need to add our own simulation pipeline and our own configuration files as well. So it was kind of tricky. And also there are a lot of modules that need to be set up. Also, the instructions were way old and they have updated the code a lot more time and it's outdated. DSP was kind of easy and it's a cleaner setup and it's available in Python. So, and all the notebooks are easy to set up. It's just plug and play. The DNA fountain was kind of old. The code is written in Python 2, and a lot of the functions and methods are outdated. So that was really difficult to implement. I was able to implement the encoding technique, but decoding is still having some issues. The shortmer combination encoding was also a good code that was a straightforward concept and was able to run properly.
Yeah, yeah, that one was easy, quick, simple to set up. So I want to go in depth about at least one of the tools. So frame D. So this is kind of how it works. So these are like the 5 main steps right here. There's data preparation, encoding, the fault injection, the decoding, and then the analysis and optimization. So the first step, the data preparation. The data is broken down into pieces called packets. And what the packets are is that it serves as a scope for the outer encoding. So there's an outer encoding and then an inner encoding as well. And with the outer encoding, it allows the user to choose the granularity for error correction, the error correction algorithm. So this is where you can kind of play around with the error correction and see what works best. So that's one of the advantages of frame D. And then the packets are then broken down into base sequences, which will then be stored on each DNA molecule. And then in the second step, encoding, the base sequences are then encoded with the outer encoding using some predefined algorithms, and then any transformations or error corrections are applied before they are ready to be stored in the DNA. So there's outer encoding back to base sequences, and then there's any transformations that need to be made, and then it gets stored into the DNA. So this is the this was the image that was in the paper, and I kind of made my own based off my understanding of it. So I drew this and this as well, like because it was a little complex here. Like there's like a lot more details, and it's a little bit blurry. It's kind of hard to see. So I just redrew it, and this is from my understanding of how the tool works. This is what I came up with. So this is how, yeah, this is how the encoding works. And then this is the fault injection. I made this as well. So in step 3, the fault injection, the simulation errors are added to the DNA. So after we encode it, we add some errors to simulate real world errors right here. So this is a pretty simple step right here. And then this is the 4th step, decoding and analysis. The DNA sequences with the newly added errors that we just did in step 3 are decoded to retrieve the original data. And this step is almost identical to the encoding, but basically in reverse. So you do the encoding backwards basically. So the inner encoding, the inner decoding, and then the outer decoding. And then step 5 is just analysis and optimization. So I guess it's not really a step, but part of the tool. But it's just another step. Once you get the results, you just analyze them and see any optimizations that you need to be made. And for the conclusions, so DNA storage is promising but complex. More work is needed to make DNA storage practical at large scale. And simulation and encoding advances together accelerate DNA storage. So not just the simulation tools, but also encoding techniques. We looked at both here, such as Frame DNA or Frame D as a simulation tool, but also DNA Fountain as an encoding technique. So we need both of them to make DNA storage better. And then each tool focuses on different priorities like simulation or encoding. They each have different designs for either flexibility, density, error modeling, or novel encoding. And DNA storage is moving toward practical use. Any questions?
Very interesting.
Yes. Uh, where? I'm not sure what this one.
It says models encoding errors and encoding, but it was basically mentioned how to actually.
I think the next slide where you have the yeah,
This?
the figure at the bottom.
No, I don't. You don't know it beforehand, but there's way like there's ways you introduce errors and like you'll see it after you decode it, but before you do the simulation, there's not I don't think there's a way to see how guess how much error. I mean, through estimation, through previous experiments, you could probably see how much error, but mainly like there's different algorithms like there's different correction algorithms that you can use to play around with the error correction and see how much error it would be, but yeah, you need to still simulate to see how much error there would be.
So going back to the next, is this what you meant about sequencing error? That you could predict and errors you would have?
Yeah, it was just
Okay.
something that I didn't really.
Their error and then
Oh,
work with simulations, certain errors, and then find out what the error was, and then
Yeah, but I think yeah, if you depending on what technology you use, you may be able to tell like what kind of errors it might have.
Yeah, for example,
Yeah.
road model. Really, do you know which location we expect which error and what type of error? For example, Lomina, we know that always the last 30 character errors.
Yeah.
So we have some kind of error and mostly substitution.
Yeah.
That's well known in advance, even before using it.
Yeah.
So we expect that to happen toward the end. So what we can do is to overlap this DNA. Some of them. And towards the last text character, we just ignore whatever there. We use the next overlapping character to cover those. This is how we correct it.
Yeah, and I think for this tool specifically, desk, we used it. It had an option for both Illumina and Nanopore. So I think we use Illumina, but we should probably test both and get more. Yeah, we could get more experiments that way and see better.
Very nice question. You have more.
Yeah, I have another question.
Mhm.
Walk me through, one back. Yeah, can you walk me through that figure?
And this is just the ease of setup, how easy it is to set up each tool. The number 5 is DSP, that's the easiest one to set up. DNA Fountain is outdated code, Python 2, and that's the least easy to set up. And Chartware is just number 4, which is the rating that we gave it. Scores right here. How easy your tool is to set up locally on your own desktop.
Yeah.
The diagonal stuff.
No, not really. It's just a score.
Yeah, I guess this is a little complex, but basically, like the farther away it is, the easier it is to set up. So you could say the closer in circles are like 1, and then the farther out is 6. So yeah, it's just a little unique way of representing it. That's a good question though.
Are you aware of any code
That uses it? Not from what I saw. I was
that
not
Microsoft
on Microsoft.
or uses
Oh,
a real device? It was
Mhm.
just kind of prototype.
yeah.
When you see it,
Uh-huh.
yeah, it would be nice if you showed that.
Oh,
Really nice. There's another project from ETH Spirit, Switzerland, that they have a bunny
yeah,
plastic 3D printed.
yeah.
Then they can melt it down, reread through scientific DNA. They could get one full 1 hour YouTube video
Mhm.
stored in that bunny.
Uh-huh.
Then when they melt it down, they could feed back that video.
Yeah.
So there are some initiatives to get it as a real product, but still we are a bit far. Especially the error thing, how to fix this.
Yeah.
And even if you know the error, over time, you don't know what happened with degradation. You can't do sequencing error. What happened over time, we still capture that.
Yeah, especially in the right conditions it has to be in. We don't know exactly what the optimal conditions are.
Exactly. So if you move that material space, for example, outer space, what will happen with radiation?
Yeah.
You move it to very hot area, you move it to very cold area, what happens? Before you read that, just scientific DNA. What happened to that? Right. That was very interesting.
Okay.